Hello everyone. So let's conclude on the hold timing analysis, and we are good to go with the setup and hold timing analysis lectures. So we concluded that the combinational delay, to start with, the combinational delay should be greater than the hold time of the capture flop. And once the clock network delay comes into the picture, if you see this particular edge, the first thing that we need to do is shift this particular edges that will reach the launch flop and the capture flop by the required amount of time. So that's what we did. So this particular clock edge, when it reaches the launch flop, it takes around 2 buffer delays, and that's basically captured as delta 1. This particular clock edge, once reaches the capture flop, it takes around three buffer delays, so that's being captured as delta 2, and the rest equations remains the same. So if you remove delta 1 on delta 2, for example, if delta 1 and delta 2 are equal, the equation still remains the same. Basically your combinational delay should be greater than the hold time. Okay, so this was about the combination, about the hold timing equation. Now to add more and more uncertainties to it, so we have assume we have a hold time of 10 picoseconds and an uncertainty of 50 picoseconds. Over here, actually, really, if you say, the uncertainty doesn't matter much, because in this case the edge that is going to the launch flop and the capture flop is the same. So the amount of jitter that will play a role for the launch flop and the capture flop will be same. For example, if this particular clock edge, let's say, doesn't arrive at 0 but at somewhere at 10 nanosecond, or sorry, 10 picosecond, this will be the arrival difference will be the same for the launch flop and the capture flop, because it's the same edge that is being going to the launch flop and capture flop. So uncertainty over here actually really doesn't matter, but still, to be on a more realistic side, we add a number which is like 50 picoseconds, a very low value for the uncertainty. So a PLL which is supplying a clock for the launch flop, it is sending the same edge to the launch flop and the capture flop. So the uncertainties and the jitter will be the same for both the clock edges that is reaching at this point and this point, because they are essentially the same. Hence the uncertainty value is kept a bit low in over here as compared to the setup time analysis, where the uncertainty was close to 90 to 100 picoseconds or even more. The uncertainty over there are even more, because there are different edges that is going to the launch flop and the capture flop. This edge goes to the launch flop and this edge goes to the capture flop. See, the amount of uncertainty is even more. In this case, since it's the same edge, things have become very simple for us, and the uncertainty can be kept as a low value. Okay. So with this numbers in place, we have to just add the uncertainty value as well. So it says that apart from the hold time requirement of this particular capture flop, I need some additional value for the uncertainty also. So please hold your data for my internal hold time and for some uncertainty value. Okay, and finally, if you want to give a name to this particular equations, it will be called as, the right hand side will be called as the data required time, and the left hand side will be called as the data arrival time. And in this case, the definition of slack will be a bit different. So slack will be said as data arrival time minus data required time, because in this case we expect the data arrival time to be greater than data required time. As in, this is in contrast with the setup timing analysis, where the data required time was expected to be greater than data arrival time, or the other way around, the data arrival time was supposed to be less than data required time. Remember, it was the combinational delay theta should be less than t. That was a requirement in the case of setup timing analysis. But in this case, since the arrival time, the requirement becomes a bit different. In this case, the arrival time is expected to be greater than the data required time, and the difference is referred to as slack. And as it is, the slack is expected to be either positive or 0. If the slack goes to negative, it is referred to as a violation, and if it goes to a negative value, it says that the data arrival is much before the data required time, which means your combinational delay is very fast. Basically this if this time goes less than the data required time, your delay is very fast and we have to slow down. That's what it actually means.